Welcome to Chapter 14. This is 14 and we're going to 17. The end is in sight. In this chapter we're going to look at acids and bases. There are two definitions that we'll focus on when trying to classify a particle as an acid or base. The first is called the Arrhenius definition. This works out really great for strong acids and bases. It says an acid is a particle that produces hydrogen ions in solution. So a strong acid, something like hydrochloric acid, will obviously dissociate to form hydrogen and chlorine. If one of those ions is hydrogen, the solution is considered acidic. And especially with a strong acid, where this thing dissociates 100%, 100% dissociation, we should get a significant amount of hydrogen formed. If I started with like 1 mole of HCl per liter of solution, I should get 1 mole of hydrogen ions. Same kind of gig with the bases. The Arrhenius definition says a base should produce hydroxide in solution. So it's really obvious if you have a strong base like sodium hydroxide or any aqueous hydroxide compound, this will dissociate 100% dissociation. So again, one of my particles produced is obviously hydroxide. The acid produces hydrogen, the base produces hydroxide. Works out great for strong acids and bases. It makes it really easy to look at a formula and predict if the solution is acidic or basic. It's a little bit tricky if you have a weak acid or base. A weak acid doesn't necessarily start with hydrogen. A weak base doesn't necessarily end with hydroxide. For example, the most common weak base is probably this guy, Ammonia Nh3. Great example of a weak base. If you have a solution, technically ammonia is usually a gas, but we often dissolve it in water. So if that ammonia is in water, here's kind of what happens. Let's look at the ammonia Lewis structure. And then I got the little hydrogen, 1, 2, 3. Here's my Lewis structure. This is going to be one of those trigonal pyramid molecules. And no matter how I look at it, there's kind of a general pull for the electrons to be closer to the nitrogen. Those are polar bonds with nitrogen having a higher electronegativity. So the electrons shared between nitrogen and hydrogen are drawn toward the nitrogen, making him somewhat negative. So we usually see this with one of those little partial negatives on top of the nitrogen. Plus, there's a lone pair of electrons sitting up on top of nitrogen. Last time I checked, electrons are negative. So there's no doubt that the nitrogen end of this molecule is slightly negative, which means the nitrogen end of this molecule is attracted to things that are positive. Oh, so what if I put ammonia in water? Do you remember a water molecule? Let's just draw a Lewis structure. This is great. Blast from the past. In a water molecule, kind of the same thing, where you've got these lone pairs of electrons on your oxygen, plus oxygen has a really high electronegativity. So the electrons in those bonds are drawn toward oxygen, and there's lone pairs of electrons. So the oxygen end of the molecule is slightly negative, and that leaves these hydrogens slightly positive. So if you have this ammonia molecule in water, the partial negative nitrogen is attracted to the partial positive hydrogen. So much so that there's often a little transfer of hydrogen, that you'll get one product being NH4 plus. Oh, that's that ammonium ion. We could say plus 1. If you transfer a hydrogen, then you're left with 1 oxygen and 1 hydrogen. And we often write that as, boom, hydroxide. Okay, so a lot of people struggle with this one because they look at ammonia, NH3, and maybe at first glance they'll say, I don't know, acid? Like there's hydrogen in it. There's definitely not hydroxide in the formula. But this Arrhenius definition just says that the base should produce hydroxide ions. So if you look at the whole equation, oh yeah, one of the ions produced is hydroxide. This solution is a base. The hydroxide's not necessarily coming from the ammonia like it is in sodium hydroxide. Sodium hydroxide is a direct hydroxide donor. In the case of the weak base, the hydroxide is actually coming from the water in solution. But no matter what, there's hydroxide produced. So when you have ammonia in solution, the final product is basic. So we'd still say that ammonia is a base. Hydroxide is produced. Okay, let's look at another definition. This one's called Bronsted-Lowry, a couple Scandinavians. Bronsted and Lowry said that acids are hydrogen donors. Well, again, that makes it easy if it's something that you recognize quickly. Oh, yeah, that's an acid. You know, like if you recognize HCl as a strong acid, it dissociates completely to form hydrogen and chlorine. Oh, yeah, it's a hydrogen donor. Piece of cake. Everybody would guess that HCl is acidic. It produces hydrogen, it donates hydrogen in solution. What about this guy? What if you had NH4? What if you had a solution? Maybe it was originally something like, I don't know, what if this was like ammonium chloride? NH4Cl. And the ammonium chloride will dissociate to form ammonium ions and chlorine ions. Guess what happens to that ammonium in solution? It can dissociate. It can produce NH3 and hydrogen. Oh. So again, we might not say that the ammonium ion is acidic. Like that might not be my first thought. A solution of ammonium chloride is slightly acidic, really? Because there's nothing that starts with hydrogen. There's nothing that like ends with hydroxide. Maybe people would guess it's neutral. But if one of the ions formed is hydrogen, if we're a hydrogen donor, that particle can act like an acid, which is the case here. Ammonium solutions, NH4 solutions, are often slightly acidic. There's a chance that the ammonium ion could release that extra hydrogen. Oh, cool. How about bases? Bases are hydrogen acceptors, a particle that can accept hydrogen. Okay, well, maybe an easy example. How about I have a solution with hydroxide? So maybe I have a solution with like sodium hydroxide. Everybody would guess, oh yeah, that's a base. I produce sodium ions and OH hydroxide ions. Well, guess what that hydroxide can do? That hydroxide, let's put it down here. If he's in any kind of a solution where hydrogen is present, he can pick up that hydrogen and form HOH, which is just water. Hydroxide is a hydrogen acceptor. It can remove hydrogen from the solution. It's negative. It would love to react with hydrogen, and we form a neutral product, water, which would not dissociate. So it's just a little different way of looking at it, especially this base. A base is something that can accept hydrogen. Oh, cool. Now what about another kind of crazy example? What about this? How about a solution of, oh, I don't know, maybe it's something like sodium carbonate. What if you had Na2CO3? And one of the ions is carbonate. So what if you got this guy in solution? -2. And again, what if there are hydrogen ions present? he could pick up 2 hydrogen and form this guy, H2CO3. Ah. The carbonate ion can act like a base. The carbonate ion can remove hydrogen from solution. So again, we might look at sodium carbonate and think, oh, that should be 100% neutral. There's no hydrogen, there's no hydroxide. But according to the Bronsted-Lowry definition, if you have a particle that can accept hydrogen, that can react with hydrogen, that can remove hydrogen from the solution, that particle can act like a base. So something like carbonate. Carbonate is a base. He can react with hydrogen, remove it from the solution. Cool. So now we want to look at like the entire equation. Let's look at some good ones. Some that we're kind of familiar with. When we look at Bronsted-Lowry definitions, we'll often see things listed as acids, bases, or conjugate acids and conjugate bases. Particles come in pairs. One particle can donate the hydrogen, the other particle can accept the hydrogen. Oh. Okay, so on the reactant side, let's say we're looking at this hydrochloric acid example. On the reactant side, we're going to label these particles as either acid or base. So I look at hydrochloric acid, HCl, and I think most of us would say, well, there's no doubt in my mind, this thing is an acid. And if I look at its partner on the other side, so here's hydrochloric acid, and we find its partner. Well, it probably matches with the chlorine, right? And then we say, well, what happened going forward? Oh yeah, going forward, that HCl was a hydrogen donor. We lost a hydrogen. But do you notice that these have double-sided arrows? These can go forward and reverse. The conjugates are labeled on the product side. The acid and base are on the reactant side, and they're always going to be neutral particles. I should say they're usually neutral particles. The conjugates will be listed on the product side, and they're usually charged. They're usually ions. What if that chlorine ion goes in reverse, and it wants to go back to the original HCl? So this little booger wants to go backwards. Well, what does he have to do to go back to HCl? He needs to gain a hydrogen. If chlorine can be a hydrogen acceptor, we're going to call him the conjugate base. Acids and bases come in pairs. Going forward, HCl is acidic. It's donating hydrogen. If we want to go in reverse, that chlorine ion is called a conjugate base. He would need to pick up chlorine to go back to the original HCl. All right, so check this guy in the middle then. Water. Going forward, whoa, H2O turns into H3O plus. Okay, so we look at water and we say, well, what happened to him? Water gained a hydrogen. Water is acting like a base. We're going to label water as a base. Okay, that feels really naughty, because I thought somebody told me one time that water is usually neutral. If you just have a pure sample of water with nothing else in it, then yes, water is neither acidic nor basic. Water is neutral. But this is a little different situation. We got something in the water. And now water can be a hydrogen acceptor. And now again, what if this thing goes in reverse, and this H3O says, I'm uncomfortable, I want to go back to the original water molecule. And then we say, well, what does he have to do to go backwards? He has to donate his hydrogen. Well, now H3O, we would call the conjugate acid. It's the pair to the base. Okay, so again, look at this thing. Going forward, HCl is the hydrogen donor. Where does the hydrogen go? The hydrogen ion is donated to water. Okay, so going forward, HCl is the acid, water's acting like a base. It's picking up the hydrogen. But now let's say we want to shift this in reverse. And we say, well, what has to happen in reverse? One of these extra hydrogens will go back to chlorine. So now H3O becomes the hydrogen donor. Chlorine is the hydrogen acceptor. The pair to the acid is a conjugate base. The pair to the base is the conjugate acid. They always come in pairs, and conjugate acid-base pairs only differ by a hydrogen. In one direction we have the hydrogen, in the other direction we've lost the hydrogen. So let's look at this guy, the ammonia one. This is a real common example again. Let's say this thing goes forward. Okay, so going forward, NH3, we find its partner, NH4 plus 1. Okay, so going forward, NH3 accepted a hydrogen. The hydrogen acceptor is the base. Ammonia is a base. Now, if this NH4 wants to go backwards, he's going to have to lose the hydrogen, meaning he's a hydrogen producer. We're going to call him the conjugate acid. He provides hydrogen to the solution, going in reverse, which is kind of what we mentioned above. That, yeah, I get it, like NH4, I might not guess that that particle is acidic, but it can be. It has the ability to release hydrogen into the solution. That makes it acidic. And then we can look at water. Wow, water, what's going on here? Going forward, water lost a hydrogen. A hydrogen producer, a hydrogen donor. Water's acting like an acid? You betcha. And now again, if this OH says, oh, I'm uncomfortable, I want to go back. If we shift this in reverse, now we call him the conjugate base. Which again, I would have guessed that. Oh yeah, hydroxide, that's a sign of a base. That's a sign of a base all the time. Because he's a hydrogen acceptor. So we can look at this in terms of hydrogen transfer in the solution. On the reactant side, water was the donor. One of these hydrogens was picked up by ammonia. If I wanted to shift this in reverse, the ammonium ion became the donor and gave its hydrogen back to hydroxide. So we should be familiar with these conjugate acid-base pairs. The acid and the base are labeled on the reactant side. The conjugates are on the product side, usually charged ions. Notice too that water can go both ways. Whoa, we call water amphiprotic. Amphiprotic is a particle that can act like an acid or a base. It just depends on what it's bonded to, what it's mixed with. Water can go both ways. He can be a hydrogen donor or a hydrogen acceptor. So don't feel bad if you're labeling water. Don't feel bad if you're labeling water as acid or base. I know somebody once told you that water is neutral. That's only if it's pure water. In solution with something else, water can either be a donor or an acceptor.